Alright, so we're trying to find, or trying to figure out what is implicit differentiation. In the last video, we looked to see what is f of x equals c geometrically. What does that represent? We saw that f of xy equals c is graphically a curve in the plane. And in fact, this function right here, f of xy equals 2, in this case, this f of xy is y cubed plus x squared minus 2xy. In this case, we saw it looked something like, there was kind of a big thing like this, and then it kind of came down like that, and yeah. But anyway, this was not a function, right, globally, because it didn't pass the vertical line test. But theoretically, you could break this apart, and so then you could look at this piece as one function, and then this piece as another function, and this piece as another function, and so on. So you'd break this into pieces and look at each individual piece, and then you could take the derivative of each individual piece. We want to avoid that. So we want to try to find dy over dx when we're given an expression in x and y equals a constant, when we can't solve this for y first. So we don't want to solve that for y first. And in fact, in this case, it would be very difficult to do that. Okay, so how am I going to do that? Well, recall that we've actually already done it. So how would we differentiate something like x times f of x? Well, this is a product rule, right? We had this, I think there was something like this in the quiz. So derivative of the first one is a 1 times the second plus the x times the derivative of the second. So we just have 1 times f of x plus x times f prime of x. Good. Similarly, you could differentiate something like, how about f of x cubed? Right, so this would be a chain rule, and so the derivative of f of x cubed would be 3 times your function squared, right, times the derivative of your inside function, which is f prime of x. Good. Similarly, I think we had, let's see, I had another example from our quiz. Oh yeah, maybe something like, how would you differentiate something like, how about the sine of x plus f of x? Right, so the derivative of that would be, derivative of your sine would be cosine. Then you leave your inside function alone. Then you would multiply by the derivative of your inside function. Right, and so simplifying that, you could rewrite that. Derivative of x is 1, and derivative of f is f prime. Good. So similarly, that's what we're going to do up here. We're just going to treat the y as an f of x. So you could think of this as, think of like y cubed as f of x cubed, right? And so what would the derivative be then for y cubed? So then your derivative of y cubed would be just like we did up here, right? It would be 3 times y squared times y prime. Or you could be more specific. You could say 3 times y squared times dy over dx. Right? This is saying that your differential here is the x. So you're differentiating with respect to x. So how about xy prime? Right? That would be what we would do for this top one here. And so we would think of that as x times f of x prime. Whoops. So when we differentiate, how about if I put the prime here, just so I remember what I was doing. Then the derivative here would be what? I'd need the product rule, right? 1 plus 1 times f of x plus x times f prime of x. Good, just like we did up here. But if I'm doing it as x times y, right? That would be 1 times y plus x times y prime. Good. So now let's get back to the original expression and see if we can just differentiate that directly. So let me rewrite that over on the next page to give us a little room here. So we've got y cubed plus x squared minus 2xy equals 2, and I want to find dy over dx. Okay, so this is telling me that I want to treat y as a function. And so this is telling me that x is the independent variable. So it's really important to pay attention to this notation right here, because it's telling you this is your function and this is your variable. Okay, so now when I differentiate, right, this is going to be 3y squared times y prime, just like we did before. Derivative of x squared with respect to x is 2x. Good. Minus 2 times the derivative of xy. I'll go ahead and write it this way first. And that's equal to the derivative of 2, which is 0. Okay, so just rewriting this, I'm going to go ahead and use this other notation just because you could use either notation interchangeably. Minus 2, and now the derivative of xy we said was the product rule, right? So that was 1 times y plus x times y prime, or dy over dx, equals 0. Okay, so now can we solve for dy over dx? We've got two of those terms, so let's go ahead and write those together. 3y squared dy over dx, and then minus 2x times dy over dx equals, I'm going to bring this other terms over to the other side because I want to solve eventually for dy over dx. So that's going to be, let's see, minus 2y on this side becomes 2y on this side, minus 2x, and then pulling out the dy over dx, I get 3y squared minus 2x. Good, and then dy over dx is equal to 2y minus 2x divided by 3y squared minus 2x. Good, and so it's noticeable, or what's nice about this is that we have a formula for dy over dx in terms of x and y, right? And so I can, even though my original expression was not explicitly defining y as a function of x, we can implicitly define it that way and still find a formula for the derivative. And so this is the process of implicit differentiation. The word implicit means that you're implicitly treating y as a function of x. Y is not solved in terms of x. Okay, so this is an implicit description of y as a function of x. Good, and I was able to find my derivative. Good, let's try another example before we end this video. So how about something like I just had a good example. Where did it go? How about sine of x plus y is equal to y squared cosine x, and we want to find dy over dx in terms of x and y. Okay, we just differentiate. So remember, we're treating y as a function of x, right? So this is going to be sine, let me go ahead and, I was going to rewrite it with y as a function of x, but let's go ahead and just differentiate in place. So the derivative of sine is going to be cosine. Leave your inside function alone. Then multiply by the derivative of your inside function equals, this is a product rule, so the derivative of y squared is our 2y times y prime, right? Times the second function, cosine of x, plus the first function, y squared, times the derivative of cosine, which is minus the sine. Good. Now let's fill in this last one. We have cosine of x plus y times 1 plus y prime equals 2y prime cosine of x plus y, let's just bring the minus sign out there, minus y squared sine of x. Good. Now, lastly, you would want to distribute this through and then bring all the y primes together, right? So if I have this y prime over here, that's going to be cosine of x plus y. I'll write it a little bit bigger, times y prime. Bring this one over to the other side, so that's going to be minus 2y y prime cosine of x. And then, so this cosine of x plus y I'm bringing over to this side, so that's going to be minus cosine of x plus y. And then I still have this minus y squared sine of x over here. Good. Factor out the y prime. So I have y prime times cosine of x plus y minus 2y cosine of x. And I still have this as my numerator over here, y squared sine of x. And now I just divide by this, and I get my dy over dx. dy over dx is equal to this big expression, cosine of x plus y minus y squared sine of x divided by cosine of x plus y minus 2y cosine of x. Good. So there is our expression, our derivative in terms of x. So again, we started off with this expression and we said find dy over dx in terms of x and y. And remember that this means that you're treating y as a function of x. Y is a function of x, right? And so when you're differentiating, remember that the y here, the derivative of y is going to be y prime. Okay, that's the main thing. And so, for example, differentiating y squared, we get 2y times y prime. But differentiating x squared, you would just get 2x, right? You don't have the extra term. Whoops, you don't have the extra term. Okay, so the next video we'll try a few more examples.